All right, welcome to the Big Ideas Geometry tutorial on section 10.3 using chords. So we're going to be able to use chords, which are parts of circles, to find some specific lengths within the circle and arc measures. So one thing to be aware of is that if you have within the same circle or two different circles that are congruent, any two minor arcs that are marked as congruent if and only if their corresponding chords are congruent. So if we look at this diagram down here below, we have arc AB and we have arc CD, these minor arcs. We also have chord AB and chord CD. So there are two different ABs. One of them is an arc measure and one of them is a chord. If the chords are congruent, then the arc measures are going to be congruent. So depending on the correspondency, if one of these chords is not congruent, then you cannot say that the arc measures are congruent either. So moving into a diameter of a circle, if that is perpendicular to a chord, then the diameter bisects its chord and its arc. So in this circle, you have diameter EG. Notice how it's going through the circle. Then you have chord FD. These two lines are marked as perpendicular because of the 90-degree angle between them. And since EG is your diameter and they are perpendicular, then both sections of this chord are being bisected, which means that FH is congruent to HD, along with the arc measure that connects them. So the arc FG and the arc GD are also congruent. Last one before we jump into examples. If one chord of a circle is perpendicular bisector to another chord, then the first chord is a diameter. So you have this SQ, it's a chord. You don't know if it's going through the center because there's no given point. Like on the last one, there was a given point. This one, there is not a given point, so you don't know if it's a diameter. Chord SQ and chord, what is that? TR, as that taskbar goes away. And it's intersecting at the point P. If those two chords are perpendicular bisectors, so you've got your perpendicular and these two lines of congruency to indicate that they are congruent, then SQ is a diameter. Basically, it's the just converse of theorem 10.7 to 10.8. So let's hop into our example. Remember the formatting is of those boxes should be arc measures, those curved lines. They are not getting inputted into Google Slides. So in the diagram, circle P is congruent to circle Q, so they have the same radius. You're also given that chords FG is congruent to chord JK. The arc measure of JK is 80 degrees. We need to find the arc measure of FG. Well, because both of those chords are congruent and the circles are congruent, you can then assume that the arc measure of the corresponding chords are congruent. So since the arc measure of JK is 80, you can say that the arc measure of GF is 80. And I don't know why that says 808. Maybe that 8 was supposed to be a degree symbol that I did not get inputted as well, but it's supposed to be 80 degrees. So we're looking at HK, finding the distance of HK. And then we're looking at finding the measure of the arc of HK in this given circle. So we've got what looks like diameter JL because it's going through the center. We have a chord HK that is intersecting our JL, and it's a perpendicular intersection. So since these two are perpendicular intersections, they form a 90-degree angle. Based on the perpendicular chord bisector theorem, JL bisects HK. So HN is going to be congruent to NK. Okay, you can also replace that as double the length of each one of the segments, which we know is to be 7 based on the given diagram. So the entire length is going to be 14. Now, in order to find the arc measures, because of that chord being bisected with the diameter and it being perpendicular, you know that each of those corresponding arc measures are going to be congruent to each other. So you can set up an equation where the measure of arc HJ is equal to the measure of arc JK. And you have your equation of 11x equals 70 plus x. Combine like terms, moving the positive x over to the left-hand side to get 10x, and dividing both sides by 10 to get x equals 7. However, the question does not say solve for x. It says to find the measure of hk. So we're going to plug that into both of our hj and jk to get the individual arc measures. 70 plus 7 is 77. You're going to add that to itself or multiply by 2 because you know that 2 of each of those measures equals the total. And you're going to get a total of 154 degrees for the measure of arc HK. Moving on, so in this diagram, QR is equal to ST, which is also going to be given as 16 units. We have CU is equal to 2x, and CV is equal to 5x minus 9. We're going to need to find the radius of circle C. So any of the radius could be from CW or CX. Remember, it's from any point from the center all the way to the edge of the circle. So here's how we can use some different parts of this circle to find one of the radius. So CQ is a segment where the endpoints are the center and the point. So that's an example of a radius of the circle C. Is that green line right there. Because CU is perpendicular to QR, because of that 90-degree angle, that triangle formed by this red, green, and black portion of this chord is going to be a right triangle. So then we're going to use those lengths of the chords to find the lengths of the legs, and then we're going to use that to find the hypotenuse of that triangle. So CU is given as 2x in our diagram. Because QR and ST are congruent to chords, they are also equidistant from the center. So CU is also equal to CY, or CV, sorry, because that is the one going to the chord. CY is part of the diameter. So CU is equal to CV. We know that CU is 2x. CV is 5x minus 9. Then we're just going to use algebra to solve for x. You move the 2x over to the right-hand side, 9 over to the left, and then divide both sides by 3 to get x equals 3. So since CU is equal to 2x, you plug in 3, and the length of CU is 6. We're then going to use that to find QU, which is part of that, again, that right triangle up in here. So because that diameter is perpendicular to the chord QR, it's being bisected. So whatever we know as to be UR is also equal to QR, or QU, which is half of 16 because the total of ST, which is the other chord, also equals the total of this QR. And it's being bisected, cut in half. So just that portion of QU is 8. We're then going to use the two legs of 6 and 8 in our right triangle Pythagorean theorem. You could use your formula of a squared plus b squared equals c squared, or if you recognize that this is a pair of Pythagorean triples, if that's something you want to dive a little bit more into, you can, but that can be proven by using Pythagorean's theorem. So CQ, which is a radius of this circle, is equal to 10. All right, last theorem. So in the same circle or in two different congruent circles, two chords are congruent if and only if they are equidistant from the center. So if chord AB is congruent to chord CD, then that means the distance between the chord and the center is also going to be equal.